Hi, my name is Manish Gupta, and in this video, I'm going to talk about Llama 3.1. So let's get started. Let's get started with first asking this question as to what is the architecture of Llama 3.1 models and what are they? What are they supposed to be meant for? How are they different from Llama 2 models? Okay. So Llama 3.1 model, of course, from Meta AI, they support multilinguality, coding, reasoning, and tool usage. So here you can see what are the members of this family. So it's written as Llama 3 here, but they mean Llama 3.1. So there are several members in the family. They train models of three different sizes, 8 billion, 70 billion, and 405 billion, and they provide both the pre-trained and the post-trained, that is instruction tuned versions publicly, right? So you can see that the instruction tuned versions are the fine-tuned ones, right? Instruction fine-tuned ones. Some of these are multilingual as well. So as you see, there is a non-multilingual English only 8 billion as well, Llama 3, but then there is Llama 3.1, which is basically multilingual. So of course, the Llama 3 was released previously, but this paper is about Llama 3.1, and you see they are multilingual as well. They can also handle long context. So we'll in fact talk about how long a context they can handle, but much longer than Llama 3. The instruction tuned ones can also support tool usage. And as you see, Llama 3 was released in April, but Llama 3.1 models are recently released in July. Okay. The interesting part is, although it's not mentioned in this table, they can also integrate image, video, and speech representations into Llama 3.1, and therefore, can also be used for multimodal tasks. So the way these Llama 3.1 models have been trained is in two phases, the pre-training part and the post-training part. We'll talk about that in detail on the next few slides. But just to give you an idea of the scale, these models have been pre-trained using 15 trillion multilingual tokens, which is 8 times the size of pre-training data for Llama 2. Similarly, they have been trained using 3.8 into 10 raised to 25 floating point operations, which is about 50x the compute that was used to pre-train Llama 2. Okay. Llama 3.1 herd of models have been all pre-trained using next word prediction or image captioning kind of tasks. I mean, image captioning, especially for the image or video kind of pre-training. Okay. So as part of post-training, typically what people do is to sort of do SFT, supervised fine-tuning, and people also do DPO, direct preference optimization. That is what these guys do. The idea is to tune to follow instructions aligned with human preferences, and also to improve specific capabilities around tool usage. For example, coding, tool usage, and so on. Okay, reasoning, and so on. Okay. So if you think about the broad architecture, well, it's a standard dense transformer architecture. 8 billion has 32 layers, 70 billion parameter model has 80 layers, and 405 billion parameter model, the largest guy, has 126 layers. Okay. And they follow group query attention. They follow group query attention. The vocabulary size is 128K tokens, where 100 tokens are English tokens, and these English tokens are from tick token tokenizer, and the remaining 28K are basically for multilingual purposes. And if you think about it that way, I mean, well, multilinguality essentially has much lesser number of tokens, which basically means that it's probably not going to be really awesome at inference time from a latency perspective for multilingual tokens. Right. So that's that. Of course, these three models differ in terms of their of the sizes of various things like the model dimension, attention heads, and so on. But the vocabulary size is 128K for all of them, and all of them actually use the rotary position embeddings. Okay. Now, decide the size of these models. Basically, they used scaling laws. They sort of discover that to achieve really good downstream accuracy, what you need, they tried to establish a relationship between the number of training tokens and the compute budget, and they found that 15 trillion training tokens is really good when you want to sort of train models of that size, with a compute budget of 3.8 into 10 to 5, 10 to 25. Okay. So the training for the largest model has been done on 16K H100 GPUs. That's huge, each with 80 GB HRAM. Okay. While doing training, they tried to be as efficient as they could and make best use of the GPUs. So therefore, they did 4D parallelism, tensor, pipeline, context parallelism, and as well data parallelism as well. Okay. So how are these models trained? So, in the previous slide, I talked about two phases, pre-training phase and the post-training phase. But well, so as to basically enable vision and speech, they also do three more phases: multimodal encoder pre-training, vision adapter training, and speech adapter training. So overall, five phases of training the Llama 3.1 models. Let's talk about them in detail. So language model pre-training is done using next token prediction as a loss and has been pre-trained on 15.6 trillion tokens using a context window of 8K tokens. Okay. Um, so that's pretty large in that senses. But as you will see later, the context window is increased further. Okay, so they use 15.6 trillion tokens with context window of 8K. These tokens basically comprised mainly 50% general knowledge, 25% mathematical and reasoning, 17% code tokens, 8% multilingual tokens. So a healthy mix across different types of pre-training data. Further, they continued pre-training, increasing the context window to 128K tokens in 6 stages. So basically, they started off with just 8K tokens, but so as to make it long context, so as to enable it to process long context, they increased the token window from 8K to 128K in 6 different stages. As a third subphase in language model pre-training, they also did annealing, which basically means they linearly annealed the learning rate to zero, reduced down linearly the learning rate to zero, while also upsampling data sources of very high quality. So this last phase of pre-training is specifically focused on high quality pre-training. The next training phase is post-training. Now, in post-training, as I mentioned, the idea is to align the model with human feedback and make it possible for it to follow human instructions and so on. Several rounds, specifically, they did 6 rounds of post-training using SFT and DPO, a supervised fine-tuning and instruction tuning on using direct preference optimization. This instruction tune data was obtained mostly manually, but also synthetically generated. Yeah. So again, we'll talk a little bit more detail on the next few slides about this part. But while doing language model post-training, besides SFT and TPO, they also pre-train using expert teachers, which basically enables new capabilities like tool use, reasoning, coding, and so on. They also make use of safety mitigations so as to make the model safe while doing this post-training. Okay. So basically, they pre-train using safety data. Okay, that's that. Post-train using safety data. Now, further after this, they basically enable multimodal capabilities by training a separate multimodal encoder. Okay. So in fact, they train separate multimodal encoders for images and speech. So they train image encoder on image text pairs. Of course, speech encoder has been trained on speech and text pairs where they mask out parts of the speech input and try to reconstruct. So speech encoder is pre-trained mostly on, in fact, speech data in an autoencoder kind of a manner where you mask out certain speech inputs and try to reconstruct them. So you have the language model pre-trained on the left side. You have the multimodal encoders also pre-trained. What you want is some adapters to be trained next. Okay, so therefore they do speech adapter training and vision adapter training and speech adapter training. So vision adapter training basically is about training this adapter, which is essentially cross-attention layers that feed image encoder representations into the language model. So you have image representations you want to feed into the language model. You need those cross-attention layers, which basically is called adapter. Okay. It's basically trained on text image pairs clearly, right? And the idea is that most people, when they train this adapter in other models like Lava or Mini GPT-4, they essentially freeze the large, they essentially freeze the large language model, and essentially several times they also freeze the image encoders themselves. However, in this particular case, while training the adapter, they also update the image encoder representations while freezing the large language model. Okay. Now, besides the image encoder, they also have a video encoder, and well, the video encoder is the same as image encoder. They just sample frames and encode through the same image encoder. But then they train a video adapter as well on top of the image adapter based using video text data. Okay. The last phase is speech adapter training, and here the adapter and encoder both are jointly updated in a supervised fine-tuning stage. While doing this as well, you basically ensure that you freeze the large language model. You don't really update the large language model while training these vision or speech adapters. Okay. Now, a little bit double click on what happens in this language model post-training phase. Okay. So as I mentioned, SFT and DPO happen, but there are other things that also happen, and that's what we'll talk on this slide. Okay. Now, this picture basically shows how SFT and DPO are happening. So you take the pre-trained model that you have obtained using this first phase of pre-training. You take that model, you essentially take the human prompts. So you have the prompts, you essentially, or you and you so you also have a pairwise annotated data, manual data based on binary preference. So this binary preference data could be, safety data. Hey, I prefer this over the other from a hate speech perspective, or helpfulness data, which particular answer is more helpful. Okay, any of those preference data points, and you take the pre-trained model and you train it further on this preference data so as to get a reward model. Once you have the reward model, you essentially, so from pre-trained model, you get the reward model. And how do you get this? You basically get this using manually curated, pairwise annotated data. Okay. And then you do SFT. So the way you do SFT is to take some prompts which you already have, and you take the best model from the previous round. So the first round, they do this entire round 6 times. Okay. So for the first round, you basically just take the pre-trained model, you generate k things per prompt, k generations from this model per prompt, use the reward model so as to figure out which of them are preferred versus not, do rejection sampling, and that gives you supervised fine-tuning data, which you use along with some special per capability supervised fine-tuning data. What is the special per capability fine-tuning data? Well, it's about certain experts. So basically, if you want to build in coding as a capability, or multilinguality as a capability, math and reasoning as a capability, in long context, tool usage, factuality, steerability, all of those capabilities, right? You take all of that data along with supervised fine-tuning data, so as to essentially get a supervised fine-tuned model. You then do DPO training, again using these preference pairs, so as to basically get a DPO model, a final direct preference optimized model. And again, all of these data points, when you try to get them labeled manually, you give 2 data points to a human asking which one do you prefer. Now, sometimes humans can say that, hey, I prefer this one, but reject this one. But sometimes they can also edit the answer slightly and then say, hey, I don't prefer either. I actually prefer the edited one. And so you basically use these preference data points so as to train both the reward model and also to do final DPO and get a better DPO'd model, direct preference optimized model. Okay. So as you notice, a whole bunch of human labeling is involved in each of these rounds. And well, they Meta AI being a rich company, they basically do 6 rounds of this kind of a post training. Okay. And yeah, I mean, when you think about the long context per capability SFT data, well, you could basically gather that data for different kinds of tasks like question answering, summarization, long context code reasoning, and so on. Similarly, when you think about tool usage data, a little more detail on it, they basically work in terms of making the model learn how to use search engines or Python interpreter, mathematical computation engine, and so on. Okay. So that's about how Llama 3.1 is pre-trained or post-trained and multimodal trained and so on. Okay. Now, how do Llama 3.1 models perform? So this is the main table right at the bottom here. They do a rigorous evaluation across crazy number of benchmarks, right? Different categories of benchmarks, general and NLP benchmarks, coding benchmarks, math benchmarks, reasoning benchmarks, tool usage, long context, multilingual, all capabilities have been tested. And they've been compared. I mean, there are benchmark data sets, which I'll not talk about. You can read about them in the paper. But they compare them, of course, there are 8 billion, 70 billion, and 405 billion models with similar sized other popular state-of-the-art models. Okay. And what you observe, of course, I mean, the observation is sort of obvious that in most benchmarks, these Llama 3.1 models beat the previous state-of-the-art models, even like, Nematron for 340 billion parameter model. And in some cases, actually, in fact, they also beat GPT-4o. Okay. So the latest kind of models from OpenAI. So you see, so for example, on multilinguality, GPT-4o is 90.5, their model is 91.6, and so on the MGSM benchmark. Okay. So net, the model performs Gamma 3.1 405 billion parameter model performs comparable, if not better, than GPT-4o. And the nice part is that it is publicly available on Hugging Face. You can download it and do offline computation if you have a good GPU, compute available to load those kinds of models. They also essentially test these models for safety and for how helpful they are. Okay, so let's look at this plot. So this plot basically shows false refusal rate versus violation rate. Okay, So of course you want a model to have less false refusal rate as possible. So if the input is genuine and naive, you don't want to refuse generating the output. Okay. So you want as small a value as possible for this, and you also, of course, want as less violations as possible. So this is a good area to be in. Okay. So you see basically different values here, and those values are corresponding to 8 billion and 70 billion parameter model, those series. And then you also see multiple points on those series, and they depend on how was the pre-training done. So they basically try to have a good mix of safety data and helpfulness data while doing this pre-training, and they found a very good niche point where they have less violation rate as well as less false refusal rate. Okay. Now, specifically, they try to figure out how good their models are, on the cybersecurity and chemical or biological weapon safety from an adversarial perspective. So if somebody tries to do repeated token attack or, indirect references, many shot attack, different kinds of adversarial attacks, right? How good are these models in terms of dealing with these attacks? Okay. What they observe is that, from a safety perspective, from a safety standpoint, they basically observe that, of course, GPT-4 Turbo is really awesome. So it's the most safe. But if you really think about it, Llama models, Llama 405 model is not that bad. So it's basically reasonably okay. It does reasonably okay. Of course, it performs differently across different kinds of attacks, but it does reasonably okay on many of those attacks. Okay. They also, so Llama 3.1, beside these models, besides these large language models, they also provide something called as Llama Guard 3. Now, it's a 8 billion model. So they take Llama 3.1 8 billion and they fine tune it further for safety classification. In fact, they fine tune it further on these 13 different hazard categories, as you can see them, to make sure that even if you basically get into safety issues with the original Llama 3 billion model or Llama 370 billion model, you can take the output and pass it to Llama Guard 3 and ensure that you have a very good suppressor in case there are safety issues with the generated output. Okay. There is a slide trying to explain how Llama 3.1 has been trained for images and speech. Okay. So here's our large language model. So this box basically shows the large language model, the Llama 3.1 large language model. It could be 8 billion, 70 billion, or the 405 billion model. And what you see on the left side is basically image and video kind of handling. On the right side, you see speech kind of handling. So you see for image encoder, this blue box is basically image encoder. So which can basically take either a single image or, and of course it divides into patches because it's a VIT based image encoder. It takes the image, divides into tiles and then processes each of them as a token. Okay. It can also take videos as inputs, and videos are basically divided into frames. Each frame is divided into patches, and then you linearize it and give it as input to this image encoder. Image encoder is, of course, a transform-based image encoder, has its own, initial linear transform, but then later it has several self-attention and feed-forward layers. Okay. So overall, it gives you an image encoding or a video encoding. Okay. Now, so you see, after that, what you have is this image representation if you're just processing images. But if you're basically processing videos, you basically get a representation from the video for each of those image frames. You have a representation for each of those image frames. You pass those representations to another transformer layer, a bunch of transformer layers. So as to essentially compute attention across those image frames and then come up with a video representation. So and what you end up getting is a good video representation. Okay. So overall, what you get is good image representation, a good video representation, depending on what you're trying to do. What is your input? Okay. Now, in the large language model, in the Llama 3.1 large language model, what you next do is to have cross-attention layers. Every fourth layer in case of images has a cross-attention layer, and every third layer in case of videos is a cross-attention layer. So you learn these video adapters, these cross-attention layers are adapters after all. They learn how to basically take your image representations and perform cross-attention along with the text token embeddings so as to obtain a multimodal representation from Llama 3.1. Okay. So so these cross-attention layers, which are essentially adapters, are trained separately right? While freezing the large language model, but while training your vision kind of a vision side backbones. Okay, so that's that. Now, on the right side, what you see is the speech encoder or the speech capabilities. So the input is the speech segment, and you have like the conformer block to pre-process speech and to encode the speech, and then you also have a speech adapter. So speech adapter is basically not combined with the text with the large language model using cross attention, but it is actually just given the speech tokens are directly provided as input in a concatenated manner with the text input. So speech and text are both sequenced and they're sort of close to each other in some ways, and therefore they chose not to do cross attention for speech, but actually combine it as part of early concatenation in the token embeddings themselves. Okay. So how does Llama 3.1 perform from a speech or video or image perspective? So well, here are some results. So this is image understanding performance, video understanding performance, and word error rate on speech recognition tasks. So what you observe is are the results on several multimodal data sets. These are results on typically visual question answering, but they are also results on image captioning tasks. Okay. And they have their comparisons which are done, of course, for the proposed three Llama 3.1 models, but also compared with GPT-4V and GPT-4o. As you observe, these models, the Llama models, are more or less, I mean, sometimes they perform better, sometimes they perform worse compared to GPT-4o, but they're comparable. They're not too bad. Okay. They're public, they're open source, they're publicly available for usage, unlike GPT-4o, which is basically behind the API from OpenAI, right? But they perform reasonably well. Okay. So even on video understanding across several tasks, they perform. In fact, in some cases, they perform so well that they create state of the art. That they are the state of the art. Right? On speech recognition tasks, again, as you see on several speech datasets, they give good results compared to other speech models like Whisper, Seamless, M40, and so on. So they're multilingual in nature as well, right? So they can support speech translation kind of things from multilingual perspective as well. Okay. So in summary, in this video, I talked about Llama 3.1 models, right? They're available in three different sizes, 8 billion, 70 billion, 405 billion. Both pre-trained and post-trained versions are publicly available. They support several interesting capabilities, including multilinguality, coding, reasoning, tool usage, and so on. They can integrate image, video, and speech capabilities into these models. And lastly, Meta AI also made available a new model, Llama Guard 3, to enable safety against several kinds of attacks. Okay, so that's it for this video. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.